Okay. Yeah, just a quick overview. We'll talk about definition, talk about an overview of what that definition means. I'll break down what makes up a recursive function, and then we'll go over some examples, and then I'll make you guys write a recursive function of your own. So just a little overview there. So first up, the definition of a recursive function is it is recursive if it calls itself within its own function definition. So I don't know if you can see my mouse, but you can see here in this recursive function definition, recursive function, it will do one thing and return if num is with 0, but otherwise in all other instances, it will recall itself with a modified number. So that makes up a recursive function if it calls itself. An overview of what that means. So recursion is a type of problem solving, takes a large problem that you can't solve and breaks it down into smaller problems over and over and over until you get to a small enough problem that you do know how to solve. It's called a base case. And then it solves that one and builds back up to the larger problem by combining those smaller problems that it solved. So if you are familiar with merge sort, that is an example of something that is kind of recursive, where it breaks it apart, divide and conquer style, and then merges them all back together one at a time. So this is a quick example of what that would look like. To do a factorial of 6, its factorial is multiplies every number back down to 1, right? 1 or 0. So in this instance, we would do factorial 6 is 6 times the factorial of 5, which is 5 times the factorial of 4, and so on and so forth. So it has to keep calling over and over and over until it gets to factorial of 1, which it knows is equal to 1, which it will then stick back and multiply times 2, times 3, times 4, times 5, times 6 until it gets the final answer. So the basic parts of a recursive function are the base case and the recursive call itself. So each recursive function is broken up. That is going too far forward. So the base case is the smallest possible piece of that problem that it knows how to solve. It is given its answer right away that it will then build upon its recursive calls with. The recursive call is exactly what it sounds like. In all other instances where it doesn't meet that base case, it will recall itself and try to subtract or add or whatever to get back to that base case. So this is an example of a summation where you add everything up to num, excuse me. So in this instance, we know if num is equal to 1, then we're returning 1. But in every other instance, we want to do 1 plus whatever the number is. So if we put in 5, we would do, no, it's not 5, or it's not 1, right? Recall with num minus 1 plus num. So it would be 5 plus recursive sum of 4, and so on and so forth until we hit 1. And then it would pop back up. It would say 1 plus 2 in this instance, and then 2 plus 3, and blah, blah, blah. So that's the basic part of a recursive function. One quick note is that the order doesn't matter. So you can have the base case first or the recursive call first, as long as you know which is which, that is what matters. So this is the exact same function, just written in a different order. So we have the base case on top, the recursive call on the bottom here, or the recursive call on the top and the base case on the bottom. So yeah. One quick note is that your base case has to actually make sense for what you are doing. So we know the summation sum of whatever number it is 1 plus 2 plus 3 plus up to whatever number. If our base case is outside of our range of things that make sense, say in this case, if number is equal to 100, then that doesn't make sense. So if I stick 10 into num, it will just continue to call because it will never hit our base case. It will subtract from number every single time. We'll go 10 minus 1 will be 9, and then 8, and then 7. It'll go negative 999, whatever, until you get a stack overflow and the computer gets really mad at you. So make sure your base case makes sense. So when do we use recursion? So recursion is used typically because it's a simple and clean way to write a function that you could write iteratively. Many problems are recursive in nature is another reason. So it's preferable to write a solution in that same way. So we have something like tree traversals, which most of you talked about yesterday, and Tower of Hanoi, and there are a lot of data structures that are recursive in nature as well. So if you have something that is recursive to start with, you probably don't want to step into something iterative. You can do all of these problems iteratively, but it doesn't tend to make sense to do it that way. And a lot of well-known algorithms are recursive in nature to begin with. So we have binary search, which you can do. You can do all of these iteratively, but binary search, Fibonacci sequence, factorial, these are all well-known recursive algorithms. So, and then there are a few disadvantages of recursion. So as our input increases, the space requirement grows, I think exponentially. It gets really big really fast. So if you think about how to make say a factorial call, if you plug in 5, you have to know the factorial of 4, which needs to know the factorial of 3, and so on and so forth. But for each of those calls, you have to calculate what's below it each time. So if you factorial 5, you have to factorial 4, which has to do all of those ones, and it does it for each and every single one of those. So it works, but it is impractical for a very large input. And because of all of those many function calls, you can have a really large time requirement because it has to take the time to run all of those function calls, right? And in certain instances, while it does make code cleaner, sometimes it makes it harder to understand. And you look back and you're like, why did I write it this way? I have no idea what's happening. Why am I recalling this function over and over? So it can be good or bad depending on the situation. So here are a couple of examples. Let's look at a factorial. This is an iterative version of how to sum a factorial. So we input our number here. We start with a base total, and then we loop, stepping up 1 until we hit our target number, and then we multiply our, what are we doing here? Multiply our total with our current step each time to get our factorial. We can also do this recursively, and look how much cleaner and prettier that looks. So we have our base case here. If number is equal to 1, we'll return 1. And in other situations, we will multiply our current number times the recursive factorial of number minus 1. This is doing the same thing as the last one, which, I don't know, depends on the person, but one of these looks a little nicer, I think. So we know we have to recall it every time. We know we're going to multiply it with its predecessor each time. And we know if we hit 1, we'll return 1, and then we can pop back out that way. And then here's our interactive example. Let's all write a recursive Fibonacci sequence. Yeah, so if everyone has a text editor of choice, you can pop that open. This is an example of an iterative Fibonacci, just to kind of get the juices flowing, so to speak. But yeah. Oop. I think we can probably write one together. So I will pull up my. And I'll stick this here. 1 sec. Oops, that's my own name. Okay. Sorry, I'm switching which one I'm sharing. How do I stop share? And then reshare. The Zoom is not my. Yes, okay. Everyone see my text editor? Yes, okay. Does anyone have an idea of where to start? I will make you all speak to me. Anyone have an idea of where to start? With a base case, sure. What's the base case? What do we know about the Fibonacci sequence?
It looks like from the example, the base case is if I is 1 and the result is I.
Yep, yeah. So Fibonacci sequence, if we think about it, if we remember, it's 0, 1, 1, 2, 3, 5, 8, 13, etc. So the way that the Fibonacci sequence builds is it takes the sum of the prior 2 elements, and then that will make up the third one. So in the case of the fourth element here, 2 is the sum of 1 and 1. So our base case is probably something to do with these 0 and 1s, right? So if num is equal to, that's wrong. If num 0, what should we do? Anyone? Yes, thank you. I'm in the wrong spot. Yeah. Fibonacci is a specific one. It has 2 base cases. Does everyone have an idea of where to go next?
Num is 1.
Mm-hmm. What would we return if num is 1? Anyone? Yes, thank you, Ben. So we have our base cases. In any other instance, we know that the next element will be the sum of the prior 2. So what could we return in that case? This is the recursive call. So these are the base cases.
Turn the method with num minus 1 and num minus 2.
Yes, exactly. Thank you.
So quiet.
I made everyone else mute, so.
What they said.
Yeah, here, let me turn that up. Matthew, will you repeat yourself?
Yeah, you return the Fibonacci method with num minus 1 plus the Fibonacci method with num minus 2.
Yeah, exactly. Oops. Num minus 2, and that's exactly it. So we can see in this case that the Fibonacci iteratively is a little bit garbled and it's kind of hard to understand what it's doing. It's switching numbers around here and then printing a result, and it's kind of a hassle to read. The recursive Fibonacci has 2 base cases, and otherwise it does one thing. So in my opinion, it's a much more elegant solution to this sequence. So we can do our print of fib of what, 5?
Did you talk about the condition you put in the return statement? About the num minus 1, num plus 1, or the num minus 1, num minus 2? I didn't understand.
Yeah, so in that case, what we want to do is, so the way that the Fibonacci sequence works is whatever element we are on is the sum of the previous 2 elements. So what we can do is we can stick those 2 elements into the recursive function, because we don't know what we're at. We have just stuck one single number into the Fibonacci, into our function, and we want to say, hey, give us out the 8th element in the chain. It doesn't know what the 8th element is. It doesn't know what any of those other things are. So it's going to have to calculate what those are specifically. So it will check to see if it's at either of our base cases, and then it'll recall the function if it's not. So it isn't. So it'll recall, it will calculate what the number, the recursive, it'll calculate the Fibonacci sequence number of the prior spot and the spot prior to that. But to do that, it has to call the function again. So it will call the function again and again and again for both of those numbers until it reaches either 1 or 0. And in that case, it'll return those and then come back up down the stack, I believe, however, whichever way you're looking at the stack, if it's down or up, until you get back to this call where it will sum the 2 numbers that it has returned from those. Does that make sense? Okay. And then we can do that.
I think line 16 needs to be recursive Fibonacci. Oh,
I had 2.
wait, that doesn't make any sense.
What?
24 says reaching on the recursive Fibonacci, and 16 is recursive Fib. But it still works?
Oh, thank you. Yeah, that's a different function. Oh. Thank you for catching that.
I was like,
That's from a different file. That's why it autofilled. That's fine. Let's give that a go. Oh, yeah, it doesn't work. What did I do? No, it was working earlier. Oh, it's trying to import things. That's why. Because of this. Here we go. Yeah, so it's printed the sequence for the first one because I told it to do that.
So with double base case, does that mean they both have to be that, like, set to 0 and 1? Like, the 1 and 1 won't translate because it hasn't reached 0 yet? Does that make sense?
Why are there two base cases?
Like, yeah, you have to, like, does it have to match the dual base case in order to get out?
So like, is it an and or is it an or?
Yeah.
This is for, so if you think about if you stick in 3, right? You want to know what the sum of the prior two elements are. What are the prior two elements? 0 and 1. And both of those have specific cases in the Fibonacci sequence. Like you can't add, if you're at the second element, which is 1, you can't add the prior 2 because there's only 1 before it. And same thing for the 0 before that, there's nothing before those. So you can't sum those. That's why you need those two base cases.
Okay.
Yeah. If there was only one recursive call to be made, like in the factorial one, we only need to call it once and there's only one base case.
Yeah.
So, okay. I think that's all I had.
Talking about, so like, using the example of the number 3 maybe,
Mhm.
can you talk through what exactly is happening as the number goes through?
Yes. And I pulled up something exactly for this and forgot about it. So this is good that you said that.
Because like I received the recursive function, I obviously used them in my homework earlier this week,
Mhm.
but like it's giving me back the number 5 when we give it 5, and I'm like, okay, what does that mean?
Yeah. One sec. Let's do. Okay. Let me share again. Okay. Can everyone see my Python tutor?
Yeah.
Yeah, okay. So let's visualize this code. First thing it does is it makes the function object and then it calls it. So it sticks in 3. So 3 is our number initially. It checks if it's 0, which it's not, checks if it's 1, which it's not, and it goes to our else. So it will return and make these two recursive calls. So we can see our stack here. The first one it does is recursive Fibonacci of number -1, which is 2. So it'll come back, stick 2 in here, check again if it's 0. It's not. Check again if it's 1. It's not. So it'll return again. So we're still just doing the first part. We have effectively paused. We have to recall because we're in our else statement. So we'll subtract 1 from number and go to 1. Stick number in and recall it again. If number is 0, no. Yes.
I have a question.
Yes.
So these things, these frames, the like recursive fib num3,
Mhm.
recursive fib num2, num1, are these on the stack?
This is your stack. Yeah. So this is why I was saying like it depends on which way you look at it because it's a stack, but it's upside down. So it's adding things underneath and they will disappear as we come out instead of like a stack of plates.
Inception is perfect.
Exactly. I almost put that in one of the slides. Yeah, so these are our recursive calls on the stack. So it's calling it with a new number each time. So we're checking, we're here with our third call on the stack to find num of 1. Checks to see if num is 1. It is, it'll return 1. So it has a return value here, which it will pass, it will return back to our second recursive call, num2. Right, so recursive num2 got the first part, recursive of number -1. Once we popped back out with that return 1 here, it continued on to the plus recursive fib of num minus 2. So that's why we have 0 here. So it's checking, it will return 0, it'll come back. We have our num of 2 call on the stack. It has its recursive fib of num minus 1, which returned 1, plus its recursive fib of num minus 2, which returned 0. It summed those and returned that, so we got 1. Now it will return back to our recursive fib of num 3 on the second half of it, because it got a 1 back from this. So it will go calculate recursive fib of num minus 2, which is 1. So we can see why this maybe wouldn't be the best solution in every situation, because it has to calculate all of these things every single time. It's checking if num is 0. No. Is num 1? Yes, it returns 1. So that's the second half of the call here for recursive fib of num 3. It'll return 1, which sums with 1 and 1. We get 2, and then we print. And that's the end of that if we stick 3 in. Did that make sense? No?
No,
Okay.
but you can go over it again later.
Okay. Does anyone else have any questions? No? Good? We call it good?
So basically that recursive call, I'm used to it calling itself, right?
Mhm.
You know, sticking something in that little
Mhm.
in parentheses,
Yes.
going back up and then going again.
Mhm.
But what you have is a double recursive call.
Yes, so that's why it had to do that
Pops it out
twice.
there, and then it adds it,
Yeah,
and then it comes back around.
yes, yeah, so for each call that it makes, it will call twice. And it'll calculate all of those every single time, come back up, add those, and then if it has to like go back up further, it'll calculate as it goes. For each time, it will make 2 calls
Yes.
to itself. So you can see why that would take a lot of time and space at a really high, really large input.
Totally.
So
Interesting.
yeah, which is one of the issues with recursion, and specifically Fibonacci. There are ways to cheat this, and things like memoization, where you basically record every single answer along the way, so then you can
So
just refer to
Into
it
an
later,
array, basically, or something like that?
something like that.
Yeah. Okay.
But that's you'll talk about that in algorithms.
I knew it was gonna be fun an hour.
Anyone have any other questions? Cool, awesome. Thanks for coming. Oh yeah, but thank you.
So your take home